Good afternoon and welcome to our webcast today. With our partner DataRay, we will talk about the topic from laser sources to software, the key factors for beam profiling. That's our agenda for today. First, I will give a short introduction on Laser 2000 and on the products from DataRay. Afterwards, I am happy to introduce you to Logan from DataRay, who will give you an insight of beam profiling. And at the end, we will have a question and answer session. To enter your question, please use the chat function in the control panel. We will answer all questions at the end of this webcast. So, Laser 2000 has more than 30 years experience in photonics. We are working with manufacturers from all over the world to provide their products to our local customers. We have also contacts in France, Iberia, Scandinavia, and partners in Benelux and UK. With our wide range of products, for example, in the laser safety, optics, fiber optics, and of course, the optical test and measurement, we provide all products to our customers and are able to cover individual needs and individual solutions for all our customers, no matter how special they are. That's our know-how and that's our passion. To give a short overview of our products from DataRay, we have here a slide with our products. So we see the cameras. We can cover the wavelength range from 190 to 16 micron. We also have slit scanners for very small beam diameters, accessories like translation stages. Together with our cameras, we are able to provide a complete M-square measurement solution, and also our specialized beam profiling systems, for example, the line laser beam profiling system, which contains also of a stage and a camera. With this system, for example, line lasers can be measured up to 1 meter. Now I'm happy to introduce you to my colleague from DataRay, Logan. Welcome, Logan.
How's everybody doing today? Thanks so much for joining me today. It's really great to talk to you guys. Today, the title of our presentation is From Laser Sources to Software, the Key Factors to Beam Profiling. Okay, so for our agenda today, we're just going to go into a very brief overview of our company, DataRay. We're going to explain some overview of beam profiling, including the industries where this is important, as well as why beam profiling is important to begin with. So when selecting a profiler, we're going to go into some key parameters you should consider. We'll also go into some differences between scanning slit and camera profilers. From there, we'll do an overview of some common measurements in beam profiling. We're going to go into a few very common measurements to give some more physical idea of what they mean exactly and how you measure those. Lastly, we have a beam profiling demonstration available. This is a video where you can find on, I believe it's on Laser 2000's website. If it's not there yet, we'll include that later. So let's get started. So DataRay was founded in 1988. We design, manufacture, and support all of our products in the US from Redding, California. Redding is in northern California, almost Oregon. So we sell internationally with the help from our distributors like Laser 2000. So for today's webinar, actually Lauren's not here today. I'll be the only presenter, but my name is Logan Hatsunaka. I'm a sales engineer here. It's great to meet everybody. Okay, so for a general beam profiling overview, a lot of people see a laser and they look at the power of the laser. That's really only one metric we're considering here, right? So if we know more details about the characteristics of our beam, we can make better processes. If we understand how we can manipulate these beams better, exactly with the beam that we're looking at, we can make better products. So how do we choose an appropriate beam profiler? What measurements do I need to take? And how can I make these measurements? These are all issues that we're going to touch on today. Waiting on this side, there we go. Okay, so beam profiling is all around us. Essentially, wherever you have a laser, you'll have beam profiling. This could be included with telecommunications, such as fiber optic cables. So we have additive and subtractive manufacturing, laser etching, consumer devices such as optical mice, laser manufacturing and qualification, LiDAR measurements like you see here for augmented reality, virtual reality, and sensing. We also have spectroscopy and 3D scanning, particle detection, LEDs, whether it be from interior lighting and car headlights, as well as biomedical applications such as eye surgery, laser surgery, and internal tracking, and biomedical applications such as that. So when we're selecting a profiler, there's a lot of key parameters we need to look at. The two most important ones are the wavelength and the proximate beam diameter. We have this plot on the left side of the screen you see here. It has beam diameter as the y-axis and the wavelength on the x-axis. So depending on what region your wavelength and beam diameter fall in, you have different options when it comes to beam profiling. For example, if your beam diameter and wavelength fall in this blue envelope on this graph, a CMOS or a CCD camera profiler might be a good idea. For different wavelengths and beam diameters, we have different regions. So for a scanning SIP profiler with a silicon detector, this might be a good region. You might ask yourself, those two regions overlap. How do I know which one to pick? We'll go into the difference between scanning slit and camera profilers in a little bit, so that'll help. So to keep going with this idea, if we're in this region, a scanning slit profiler with an in-gas detector might be a good option. And finally, if we're over in this region, a microbolometer IR camera might be a good choice. So in addition to wavelength and beam diameter, we have other key parameters when choosing your beam profiler. We need to make sure that attenuation will be adequate so we don't damage anything. So for continuous wave lasers, the average power is important. For pulse energy lasers, the pulse energy, the pulse repetition rate, and the pulse width are important for figuring out attenuation. When considering a profiler, we also recommend considering what kind of measurements you want to make. There's single or multi-plane profilers out there. So if you know exactly what you need to measure, sometimes it's less expensive to know that upfront. So we were just talking about the difference between scanning slit versus camera profilers, and here we're going to actually go into some of those details. On the left side of the screen, you see one of our profilers, the DataRay WinCam D LCM. This is a camera-based profiler with a global shutter. It'll provide true 2D images of your beam, such as the image shown on your left here. So it has pixel by pixel mapping. So it's a full 2D image. You can draw an axis across it and just read the pixels out pixel by pixel to get a line profile in that direction. So really useful. To contrast with that, a scanning slit profiler uses a scanning slit that we move across the cross section of a beam. This gives us a one-dimensional profile. So you can do this in X and Y orthogonally and get an X and Y profile. If the slit is large compared to the beam, you can do knife edge measurements, such as the plot shown on the right. The differential of these results will give you a one-dimensional profile. So if we look at the left side of our screen, we have a camera profiler. To get a one-dimensional profile, we just read out those pixels individually. So as we see, if we go vertically, we just look at each pixel, and that'll give us a profile in that dimension, or in that axis, so to speak. Where this differs is on the right side with a scanning slit profiler, you're using an entire slit just to get one intensity point. So it's essentially a summed measurement. We're using an entire vertical column of quote unquote pixels, entire vertical column of the beam to get only one measurement. So something really important to point out here is you'll notice on the right side, those little minimums, those little black dots where the intensity drops, they're not represented well in the scanning slit profile. This is because scanning slit profilers, when you have non-Gaussian behavior, higher order modes or hotspots, scanning slit profilers can mask this or not show it as well. So with that in mind, we have a few additional pros and cons for scanning slit profilers. In general, the beam is focused onto a set of slits, not directly onto a detector. So you generally need less attenuation than camera-based systems. They're really well suited for focused spots because they can go down to very small diameters, down to 2 microns with knife edge mode. We have in-gas detectors available as well as dual detectors, so you can cover a lot of wavelength range with only one unit, which is very useful. You can also go into that 1550 nanometer range fairly inexpensively. Some cons, as we saw, the summed profiles are the only thing you'll get with this. You're not getting a true 2D profile of your beam. The measurements are time averaged, so this isn't really useful for low pulse repetition beams. It's also not suited for multi-mode or asymmetric beams, as we saw with that masking behavior. So going in a little bit deeper with camera profilers, skipped ahead one too far. So some additional pros and cons for camera profilers. As we talked about, you get a true 2D dimensional mapping of the energy distribution. Global shutters are available, which allows you to go down to very low pulse repetition rates and still capture single pulse beams. It's really well suited for non-Gaussian beams because you have that full 2D image. It's also suited well for multi-mode beams for that same reason. Generally, the beam is focused directly onto the sensor or is aimed directly on the sensor. So this requires more attenuation generally. You have a lower optical dynamic range with cameras, and the resolution is limited by the pixel size. So you can't go down to as small as beams as you can with a scanning slit profiler. Fringing is also possible in some configurations. So we have some common profiling measurements we're going to go ahead and talk about. When you're choosing a profiler, it's generally a good idea to keep in what you want to measure in mind. So this is just a list of common measurements we see a lot. In this presentation, we're going to go into a few of these and explain their physical significance, as well as go into how you would measure them. So we have beam size, which is really common, diameter measurements, the shape, whether it's Gaussian or top hat or anything else, the position of the beam, beam alignment and beam stability. Beam propagation is usually really important, measured by the beam quality m squared or the propagation ratio m squared, and the divergence is common. You also look at focus location, mode structure problems, hotspots, interference. You can also see if you have any stray or satellite beams from some reflection or something else. So to go into some of these measurements a little bit more, we're going to start with something very, very common. Diameter measurements in beam profiling are one of the most common measurements. There's various diameters for a beam diameter. Because the tails of a truly perfect Gaussian beam will trail on for a long time, we have to set a limit where we can define the beam edges. So 1 over E squared is a very common method for this. Full width at half maximum and D4 sigma, also very common. Since 1 over E squared is so common, we're going to go into a little example here showing how you exactly mathematically find those beam limits. So if we have a perfectly Gaussian beam on the left graph, we can define the 1 over E squared beam limit as 13.5% of the peak energy. So we draw a horizontal line at 13.5%, and then we can draw vertical lines down from there to find the beam limits. In this case, we have one beam limit at 29.9 microns and another at 70.1 microns. So the difference in that will give you the diameter of 40.2 microns. So there's various other clip levels and beam diameter definitions based off of that peak percentage of the intensity. So another one is full width half maximum. The way you find these diameters is very similar to the way you'd find 1/e squared. The only main difference is that you're using a 50% irradiance. So like we did before, we have a perfectly Gaussian beam on our left plot. In the middle plot, we draw a horizontal line at 50% intensity, and then we draw two vertical lines down from there to get the edges of the beam. Here you'll see that the diameter is 23.6 microns. So in addition to these percent intensity clip levels, we also have other methods of determining the diameter. So D4 sigma diameter is a very common one used in ISO 11146. It's based on the standard deviation of the entire profile. So you get the entire profile, find the standard deviation, and multiply that by 4 to find this diameter. It's interesting to account for, since like we talked about before, these perfect Gaussian tails come down. The standard deviation takes those into account. So this diameter inherently takes the tails into account a little bit more. So now that we've talked about typical diameter measurements, we can go into go a little bit deeper. So divergence is another very, very common measurement to define the propagation of your beam. It measures how quickly a beam will diverge in the far field. So the far field is 4 Rayleigh lengths away from the beam waist. I've included a diagram on the right to show generally what we're talking about. The beam is coming in from the left, is focused into the beam waist, and then diverges into the far field. The divergence, the full angle divergence is highlighted in red in this diagram and shows you physically what that means. So to measure the diameter, we have various different options. They generally fall into either a single plane measurement or a multi-plane measurement. And all that means is we're making one beam profile or making multiple beam profiles along the axis of propagation. So, and we're going to go into a few of those right now. So for a single plane divergence calculation, this is one simple way to do it. If you have a diverging source and you know the distance z from the beam waist to the sensor, and you profile the beam, you'll find the diameter. And from that and some trigonometry, you can quickly find your full angle divergence. And that equation down there is just based off of a little bit trigonometry. Essentially what this means is, from a single beam profiling measurement, if I know the beam waist to sensor distance z and the diameter of my beam d, really easy to calculate your divergence. Another single plane divergence calculation method, it's only for Gaussian beams, but Gaussian beams have the unique ability to have their divergence measured through this really simple method. Essentially, we have a beam coming in from the left, it's focused by a lens, and then we measure the diameter of the beam at that back focal length. That diameter, in this case, we're calling it 2W, is the D4 sigma diameter we just discussed earlier. So once you measure that diameter, you just divide it by the focal length, and you have a very quick way to find the divergence. These systems are really, really useful for collimated or low divergence applications in situations where it'd be very difficult to incorporate multi-plane divergence measurement. So some more common profiling measurements. So for divergence, we've talked about 2 single plane measurements, but this is, we can also do it with using a multi-plane measurement method. We usually do this by attaching a profiler to a translation stage. Here on the top right, you see a WinCam D LCM attached to one of our M2DU translation stages. The translation stage moves in the axis of propagation and takes many beam profiles across it. Typically in our DataRay software, you can show this as this caustic 3D view in the bottom right, showing the multiple beam profiles. And from this, you can calculate divergence pretty straightforward. So moving on from divergence measurements, another really common beam propagation characteristic is the m-squared value. We call this beam quality. It's also known as the beam propagation ratio. So if you hear those different terms, they're the same thing. The m-squared of a beam is greater than or equal to 1, where if it equals 1, it corresponds to a perfectly Gaussian beam. So as you increase m-squared from there, you'll increase the beam waist and the divergence of the beam will increase. So for a given ideal beam waist, as m-squared increases, you get higher divergence and higher beam wastes. And you can see that on this graphic we've included to the right, showing the behavior of the beam as the quality goes down. So to measure m-squared, generally we incorporate another profiler on a translation stage. In this case, I'm showing you the same WinCam DLCM and M2DU translation stage. It's doing the same basic idea, traveling in the Z direction and measuring many different beam profiles. One difference here is the beam waist needs to be accessible to make these measurements. If the beam waist isn't accessible as it is, you can use an extra focusing lens. The idea being you want to basically put the beam waist somewhere along that translation stage so we can get points before the beam waist, near the beam waist, and after the beam waist in the far field. The exact way that you calculate m-squared from these profiles is a little bit beyond the scope of this presentation. If you have any questions, you can contact us. But essentially, what you need to know is after you make all these measurements, the DataRay software will calculate m-squared automatically. So what if your beam isn't even a spot, right? What if you have a line laser, for example? You can absolutely profile these measurements, these types of lasers, excuse me, but we have to incorporate a specialized system. So in this case, on the bottom left, you see our line laser profiling system, which is one specialized system you could use for this. It's similar to what you saw in the divergence and m-squared measurements, except in this, you don't need a lens or anything, and you're essentially just rotating the camera in the translation stage. So now instead of profiling along the axis of propagation, it's profiling along the line, your line laser. From this, you can get the width of the beam, you can get normalized intensity distributions and centroid offsets. On the top right, you see just a full line profile from our software. It's 200 millimeters long and 1.1 millimeters wide. And then below that, you see a 4x zoom and a 16 times zoom. In the 16 times zoom, you can see a lot of really small details that would probably be hard to know that you had if you hadn't profiled this line laser. One more consideration, it comes up a lot, is if you have a large or highly divergent beam. So with large and highly divergent beams, by the time you can profile them, their diameter is generally quite large. This necessitates either a large active measurement area or something else. So we have specialized systems available for these large profiling systems. Instead of using a large sensor or something like that, it's a transmissive screen that's illuminated by the beam. So essentially the beam will come in, illuminate the transmissive screen, and from the opposite side, a lens and profiler will then re-image and profile that transmissive screen. So since the screen is so big at 200 by 200 millimeters, you can really capture those highly divergent beams or large diameter beams quite easily. So we have a beam profiling demonstration available. It'll be available as a video through Laser 2000, but we use the WinCam-D LCM with a fiber optic cable and a 635 nanometer source for part of this demonstration. The WinCam-D LCM has a CMOS sensor, wavelength from 355 to 1150 nanometers, and an active measurements area of 11.3 by 11.3 millimeters. We show you a lot of DataRay's really full-featured software. We talk about a lot of this stuff that we've talked about today with diameter measurements, and hopefully in the future we can build on that as well. So they will have more information on you where you can find that video. And I think that's it for me, and I really appreciate your time. I'm open to questions if anyone has them. Thanks for listening, everybody. I believe Laser 2000 is going to take it back. There it is.
Hi,
How you doing?
Logan. Thank you very much.
Hi. Absolutely.
It was a very interesting webcast and a very informative topic. I think it's very important for all of us to know what is important to make the right choice for his application. And finally, I'm happy that everything worked out. So we can start with the question and answer session.
Great.
So first question, how many beams can be measured simultaneously with a camera?
So that'll vary depending on the manufacturer. DataRay software, we allow for up to 8 simultaneous beams on our camera profilers. That would be another pro and con of a camera versus scanning slit profiler. With scanning slits, it would be a lot more challenging to profile multiple beams, but with camera profilers, it's absolutely possible.
Okay. Thank you.
Yeah, and if you have any questions, you can contact us, sales@DataRay, and I can give you some documentation.
Another one I have here. Okay. Is the stage fully integrated into your software?
Yes, absolutely. So for M² measurements, the process is very straightforward, well documented in our manuals, but essentially the process is automated. It'll adjust exposure time and make sure the profile is stable before it goes to the next one. It'll do multiple different measurements and figure out exactly where it needs to put those measurements in order to give you a valid result. So really straightforward, absolutely.
A short add-on on this, the software is full with different kind of options you have. You can watch the beam wander. You can plot your Gaussian beam to your
Absolutely.
beam. It is a full-featured beam profiling software for all DataRay equipment.
Absolutely, and in that demo video that will be available soon, we show some of those beam wander features and stuff like that. And it's also important to point out, if you buy a DataRay profiler, you get as much software as you want. You can put it on all of your computers if you want. Yep.
Yeah, so there's no license you need for the software.
Absolutely.
Okay, I have another one. I will copy it in. So, how many Z position beams have to be taken to receive an isoconform M² measurement?
Off the top of my head, I'm not sure if I remember. I believe it's 10 on both sides. It's 10 within a certain amount of Rayleigh lengths, and it's 10 outside. If you contact Laser 2000 or me, I can look up that exact number. It's something like that. You generally want the same amount of Z profiles before the beam waist and after the beam waist to make sure that gives you an accurate measurement. Yeah.
And therefore, you also offer different lengths of stages, like the 50 millimeters, the 200 millimeters, and the latest one we now have is a 1 meter stage, which will cover for sure most needs.
Absolutely, yeah. And the DataRay software will look at whether you have a 50, 200, or 1,000 millimeter stage. It'll find the right increments, Z increments for to give you a valid ISO 11146 measurement.
Okay. Then, Logan, thank you again very much for this very interesting webcast and informative explanation what we have to consider while measuring a beam profile and the M-square. What is very important to have a reproducible, yeah.
Absolutely, and I'm glad everyone could come and join us. I think this has been really helpful. If you have any questions on anything, contact Laser 2000 or us, and we'll make sure you get all the help you need. I really appreciate everyone being here. Hopefully we can do some more of these in the future as well. All right, I think if that's all the questions, I appreciate everyone. Have a nice day.
Thank you, Logan.
Take care, everybody. Once the WinCam-D LCM is set up and the DataRay software is running, you're ready to start profiling. To begin capturing frames, press Ready or the Go button here. 2D profiles are almost immediately generated. Here we have a false color 2D plot. Below we have two one-dimensional profiles. Each of these corresponds to one axis along the crosshairs shown here. If we right-click this plot, we can auto-orient the crosshairs or change them to some degree. This page has significant important information. The major and minor diameters are shown here, the mean diameter, the effective diameter, the ellipticity of the beam, the orientation of the beam, the orientation of the crosshairs, as well as the centroid location. You can change the centroid positioning from absolute to relative by clicking here. The ADC peak percent is located here, and the plateau uniformity is located here. At the top left, we have the option of selecting two different clip levels. If I click Clip A, I'm able to select 1/E squared, full width half maximum, 86.5%, or some other custom clip level. You can also select D4 sigma diameters here. The exposure time can be automatically adjusted, but in some cases, you might want to use a manual exposure time. You can right-click here and disable auto exposure adjustment, and then adjust the exposure time accordingly. At long exposure times, the sensor becomes oversaturated. The orange text shows these results are unreliable and either more attenuation or a lower exposure time is required. And now Lauren will show you some more features using an XYZ stage and the WinCam-D LCM.
The current setup uses a 405 nanometer source that is collimated at 4.6 millimeters using a collimation lens attached to the fiber output. I can move the fiber up and down with its lens using the XY stage that I have mounted the fiber and lens on. You can see that there is large diffraction circles that are moving up and down with the beam. These circles are a result of dust on the lens, which I can tell is on the lens because it is moving with the beam as I move it up and down. There are also smaller diffraction spots. These do not move as I move the lens, and these spots are as a result from dust on the ND filter, which is attached to the WinCam-D-LCM camera. You can see as I rotate the filter, those spots will move. It is recommended to remove dust using a stream of clean air. The Beam Wander dialog can be opened using the green target icon on the toolbar. It continuously records data, so I will choose Clear to begin with a clean plot. The Beam Wander dialog plots the X and Y centroids on a target to track the position of the beam centroid across frames. I can move the beam left and right or up and down, and the Beam Wander dialog will show the path on its plots. You may want to disable averaging when recording a beam wander measurement if you would like to measure the beam stability of your laser, because averaging can average the centroid measurements, which you may not be interested in doing if you're measuring stability. Older points are darkened and newer points are shown in a brighter red color. You can also record beam wander in pointing angle instead of X and Y microns. You can do this by opening the Clip A level entry dialog and choosing Enable Pointing. Enter the source to imager distance, which the software will use to calculate the pointing angle using the geometry of your system. The software will now display pointing based on the distance you entered and how far away the centroid is from the center of the sensor. You can also choose the relative centroid button and change the what part of the sensor will correspond with a pointing of 0, 0. The pointing angle will show in the beam wander dialog in addition to the typical X and Y spatial distance measurements. The strip chart dialog is a useful feature to plot any of the output values the software measures over time on a graph that can be exported or saved. You open the dialog using the toolbar icon and choose up to 4 points for each of the plots to record. I will choose the beam width 2WUA, which is the beam width across the U axis at the clip A level. I will choose start to begin the measurements, and the diameter will record over time on the plots. I can begin to block the beam to artificially change its diameter, and we could see that the plots will show the diameter change on the graph. There are options to export to CSV or Excel. There's also an option to generate a report which shows an image of the plots along with any notes and measurement values from your measurement.